A transmission line is a cable that connects a transmitter to the antenna, and it must match both so as to get the maximum signal sent out into space. The characteristic impedance of the cable is determined by the inductance and capacitance. In this case, the square root of L divided by C, which would give us 25.8 ohms, and no matter how long the cable is, it will always have the same impedance. The impedance of a coaxial cable is determined by the diameter of the inner conductor and the diameter of the dielectric material surrounding the inner conductor. And then epsilon in this case is 2.3, which is for polypropylene. Then using the formula shown, you can calculate the impedance, in this case 98.1 ohms, and once again, no matter how long the cable is, the impedance will be the same. Open wire is used for more powerful transmitters, and the impedance depends on the spacing of the bare wires and then the gauge of the bare wires. In this case, the formula is simplified because the epsilon is equal to 1 because the conductors are exposed to open air. And so the epsilon of air equals 1. Waveguides are hollow tubes that are used at higher frequencies. The frequencies of operations are determined by the physical dimensions of the waveguide. The first formula you see, lambda equals 2x divided by m, determines the cutoff wavelength, or the longest wavelength that can be put through this waveguide of this particular dimension. Once you find the wavelength, then you can calculate the frequency with the second formula, f equals c over lambda, in this case 17.6 gigahertz. M, the mode, refers to the orientation of the E field with respect to the M field. Usually they use mode 1. Here is another example to find the shortest dominant wavelength, or else the highest frequency that we can put through the waveguide. Once again, first find the wavelength and then the frequency, in this case 49.5 gigahertz. Also, I should mention that all these calculations must be done in meters. If the dimensions are given to you in centimeters, first convert to meters before applying the formulas. The purpose of the electrical length is to see if the transmission line is of the right size to accommodate the signal that we're trying to transmit. In this example, let's say we have a frequency of 125 megahertz, and we notice that the speed now is less than the speed of light, in this case 0.75 c. If the transmission line is 5 meters, will it accommodate the signal? When we go through the formula, we see that the electrical length is 2.78 lambda. The 0.78 means that the signal is too long, and so we have a mismatch. When you have a mismatch, the signal bounces back and creates standing waves, which can cause a major problem. In this problem, we're trying to transmit the FM band, and we calculate that the center frequency of FM is 98 megahertz. And then we know that the electrical length should be 0.25 lambda for good coupling. So we know that the frequency is 98 megahertz and the speed is 0.8 c. So the only thing we need is the length. So what we do is we rearrange the electrical length formula so as to solve for the length. Once we solve for the length, we see it's 0.621 meters. So what they do is they take the cable, they cut it to 0.612 meters, and then connect it to the antenna, and hopefully you'll get good coupling. Standing waves are created when there's a mismatch between the transmission line and the antenna. In this case, we can calculate the standing wave reflected ratio with the formula if we know the impedance of the transmission line and the antenna. In this example, we calculated that the standing wave reflector ratio is 0.6. What this means is that 60% of the signal has been absorbed by the antenna and transmitted. And then the custom is once they have the ratio, then they invert it. As you can see, 1 divided by 0.6, and that's just customary. The previous problem looked at how much energy was absorbed by the antenna. This problem does the opposite. It tries to calculate how much energy has been reflected using the reflection coefficient gamma. If you look at the formula, and if we know the impedance of the transmission line and the antenna, we can calculate gamma. In this case, gamma is 0.5. That means that 50% of the energy has been reflected. Once we have calculated gamma, then we go back to standing wave reflected ratio and calculate that the ratio is 0.33. And once again, we reinverted so that the standing wave reflected ratio is 3. And then keep in mind that ideally, SWR should be 1 for a good absorption.